Yeah, thank you. Yeah, thank you, Sirian. So, can you hear me, everyone? Okay.
Yes, I can hear you.
Yeah, good afternoon, everyone. My name is Jun, and I'm currently working at NASA Goddard as a part of the Morgan State University Guest Star 2 program. I'm very pleased to have the opportunity to give a seminar today at the Statistical Learning and Atmospheric Chemistry Slack seminar series. I first met Sirian through the NASA HACast meeting at Washington University, and I truly appreciate the chance to connect again in this academic setting. I hope today's seminar will be meaningful and engaging for all of us. Yeah, although I currently work in Earth and atmospheric science, but my academic background is actually in engineering. So during my PhD, I focus on machine learning and scientific data analysis, working with the structural physical data sets rather than purely theoretical modeling. In NASA, I now apply these machine learning methodologies to air quality forecasting and environmental data simulation problems. So my current research focuses on deep imbalanced regression and regime-aware expert modeling and satellite data-based air quality forecasting model development and physically interpretable machine learning model development. And also these days I focus on partially on uncertainty analysis and quantification, try to develop the NASA's standard and guideline. Uh, I in summary, like I try to develop a reliable data-driven forecasting system that bridges physical modeling and modern AI system. Let me briefly work through the structure of today's talk. In part zero, I will give a short project introduction to provide context and motivation. In part one, I will discuss the problem of imbalanced regression and how it can distort model behavior, especially in environmental forecasting tasks. And part two, I will introduce our structural framework based on the residual expert architecture, which enable regime-aware decomposition of the prediction problem. And finally, in part three, I focus on regime behavior, reliability, and extreme events, including how we evaluate robustness under rare but high-impact scenarios. So for this seminar, I assume a basic understanding of machine learning concepts at the graduate level, and there will be some equations throughout the presentation, but I will try to keep the explanation as intuitive and structured as possible. Also, this talk is intentionally more technical and focused on machine learning methodologies. So the goal is to present a framework that can be transferable across domains rather than being limited to a single application field like air quality forecasting model only. Yeah, part zero. So our model is data-driven, leveraging over 3 years of historical GeoSAP. GeoSAP is a product of the GMAO in Goddard here, and try to provide like the next 10 days meteorological parameters and aerosol parameters. So we are using that parameters to estimate the future value as PM2.5. So that means forecasting model, right? So as shown in the figure on the left, we pre-process the GeoSAP forecast data, various aerosol and meteorological variables as an input for the next 3 days. And the framework has been expanded to provide forecasting data while also collecting and evaluating additional data from the AeroNet and OpenAQ sites, further enhancing the training and validation process. So this slide and next highlight the updates made from the initial model to the current operational version. So our initial model developed by our intern graduate students, he used only 15 input variables from the GeoSet P at a single time step. It couldn't fully leverage the CNN's dimensional data. So as a result, the forecasting accuracy was relatively low and did not meet expectations. So we therefore developed a new model, version 2, expands the input to the 3 days of GeoSAP forecast, which 8 time slot per day, totaling 360 features as a comprehensive input. So in the input array, the x-axis shows the GeoSAP variables, and the y-axis shows the 3-hour intervals, and the z-axis represents the 3 forecast days. So performing a 15 by 8 structure, the three-channel images similar to the RGB, but representing 3 days of information along the z-axis. So this expansion helped to capture the temporal continuity along the y and z and variable relationship much better, because we also consider the x as different variable features, leading to significant improvements in forecasting performances. This related study is already published in AGU Journal. And this slide presents the latest feature of our model. As I mentioned earlier, we are continuously evolving our forecasting system by replacing the older AI models with the newer, more advanced one. So on the left, you can see the model architecture. I won't go into the detail layer by layer design, but I would like to highlight that we are not simply applying a generic ML model. So we adopt a temporal convolutional network for this version 3 as our baseline architecture, which is particularly well suited for handling the time series input and output data. So the green boxes in the diagram represent the unique features of TCN structure, while the blue boxes indicate the additional components we introduced to better address the challenges of imbalanced air quality data. And in the latest model, each aerosol and meteorological variable is treated as a separate input channels. Yeah, here. So this processed information is then passed through the multiple layers, generate the continuous PM2.5 predictions as the final output. So to better capture the dependencies across different time steps, we apply the dilated causal convolution. Unlike traditional methods like LSTM, this approach is assumed that even distant time steps, like just simple 3 hours or 6 hours or 12 hours or 1 day, something like that. So allowing the model to learn the long-term temporal patterns more effectively. I will skip the data imbalance here, since I will take care of this in detail in the part 1. So just a quick note before I get into the detail. Some of the examples I'm using here are simplified to help explain the concepts more clearly. So the actual mathematical formulations are a bit more complex and may differ slightly. So please understand this. From this slide, I prepared for today's seminar for who had a specialty for machine learning or statistical approaches and hope to learn something new or interesting things. So yeah, these figures illustrate what we call the imbalanced classification problems. In many real-world data sets, class distributions are not uniform. Instead, they follow a long-tail distributions. So in the upper example, places classification, a few categories such as home or forest appear very frequently, but these are called head classes. However, many other categories such as specific buildings or rare locations appears only a small number of times. This forms the long tail. So the same phenomenon appears in the lower example, like a species classification. A few species dominate the data sets, while thousands of species have very limited samples. This imbalance creates a fundamental learning problem. Like most standard machine learning models just minimize the empirical risk, such as cross-entropy loss. Since head classes dominate the training data, the model becomes biased and toward them. So as a result, like a performance on frequent classes is very, very strong, but performance on rare classes is significantly degraded. So overall accuracy may look fine and high, but minority class performance is very poor. So this is the core challenges of imbalanced classification. So this slide shows the imbalanced regression problem. So now let's move to the regression things. So in regression, the target variable is continuous. For example, AZ in this figure, we can see that most of the samples are concentrated in the middle ranges, while very young and very old cases are much less frequent. So this uneven target distribution is what we call an imbalanced regression problem, similar to the imbalanced classification. But unlike classification, there are no discrete classes. The imbalance exists over the density of the continuous target space. As a result, like models tend to learn the dominant region well, similar to the classification problem, but perform poorly in a low density regions, especially at the extreme cases. So this often leads to systematic underestimation or smoothing of real values. So this slide shows the distribution of our real target variables, PM2.5 concentration. As you can see, the distribution is highly skewed. Most samples are concentrated in the low to moderate ranges, while high pollution levels appear very rarely. This is a continuous long-tail distribution. So the left region corresponds to the normal air quality days, but the right tail corresponds to the extreme pollution events, such as wildfire or high dust cases. So since our prediction target is continuous and the density varies dramatically across the range, so this becomes a long-tailed regression problems. So extreme events are rare, but they are the most critical cases for decision making. So let's try to use these kinds of equations from now. So let's recall the standard regression objectives. So here risk function can be defined with the fx, yi, and n, and f represent the model prediction, and y is the true target, and n is the number of samples. The square term represent the mean squared error, right? So this is the standard mean squared error objective. Importantly, this formulation is density agnostic. So each sample contributes equally and regardless of how common or rare its target values. So this becomes problematic under long-tail distributions. So this shows like a risk under the data distribution. So we can add another terms, expectation terms as a E over the joint data distributions. And then we can rewrite this expectation function with the probability function P. So regions where P is large contribute more to the integral, right? So because most PM2.5 values lie in the low density range on the left side of the figure, and those regions dominate the optimization process, right? So this leads to what we call dominance of high density region. So the model priority performance where are abundant, but these cases we need to consider using these expectation functions as well. So to correct this imbalance, we modify the loss. So loss WMSA represented the weighted mean square error. So we just replace that expectation function with the weight. Weight is just assigned to each sample, and the weight can be defined with this probability function, whatever over probability function. So samples in the very simple concept, like samples in the low density regions receive the higher weights, and samples in high density regions receive the lower weights. So in the other words, like we compensate for rarity by increasing their influence. So this idea was formalized in the many papers, but Yang et al.'s papers clarify this and how to use these functions for a better training process. So in his paper, he suggested this called label distribution smoothing algorithm. So instead of just using the raw empirical density, we just smoothed the label just using the corner functions. So in practice, I use the Gaussian corner here, but you can use any kinds of the corner functions to smooth the data distribution. So this operation performs local averaging over nearby label values. So intuitively, like rather than treating each PM2.5 being independently, we acknowledge that neighboring values are related. So on the right plot, like the green curve shows the row inverse frequency weights, and the red curve shows the smoothed LDS weight. So you can see the red curve is stable and continuous, and this stabilizes the training and prevents over the rare noise samples. And however, weighting only rescale gradients, the model still uses a single shared function to represent all regimes. So this can cause an interface between rare and dominant patterns. Scalar correction does not change model capacity allocations. So this motivates the central hypothesis. Instead of only modifying the loss, can we allocate model capacity conditionally? So this leads to the mixture of experts and residual experts modeling. That is the transition to part two. So in part two, I will just introduce the residual mixture of experts framework, which explicitly decompose the prediction problem into regime-aware components, rather than only correcting sample weights. Yeah, so let me briefly introduce the concepts of a mixture of experts. So instead of using a single global model to handle the all input cases, we can build like multiple specialized model called experts. So each expert is designed to capture the different patterns or regimes in the data. At the same time, we introduce a gating network, and the gating network takes the same input and decide how much weight to assign to each expert. The binary output is a weighted combination of expert prediction. So conceptually, experts provide specialized knowledge, and the gating network decides which expert to trust, and the output aggregate their contributions. So to build the intuition, just imagine like a consulting firm that helps companies launch new products. There are three specialists. Expert one is market trend analysis. This expert one is focusing on the demanding forecasting and industry patterns. And expert two, marketing strategist. Expert two just focusing on the designing the campaigns and customer targeting strategies. And expert three is pricing specialist, optimize the pricing based on cost and competition. At the top, there is a project manager. In machine learning terminology, this is a gating network. So, simple problem. A new client says, like, we want to launch a smart fitness watch in Europe next quarter. Now the question becomes like, should one specialist handle this, or should multiple specialists can contribute? If multiple, how much influence should each have? So this decision mechanism is exactly what the gating network does. So the first one is a hard gating. In hard gating, the project manager selects just only one expert. For example, this is primarily a pricing sensitive product, and the project is assigned only to the pricing specialist. So technically, like the gate outputs one hot vector such as 0, 0, 1. That means like we only activate the expert three's opinions or depth values, right? So advantages of this hard gating is efficient and very clear specialization, but limitation is real world problems are rarely solved using the just one dimensional problem. And case two is soft gating. In soft gating, the project manager distribute the responsibility to the or selected experts. So instead of selecting only one expert, the manager say like this project is 50% market demand, 30% marketing strategy, and 20% pricing. In that case, it's maybe the gate output continues with something like 0.5, 0.3, and 0.2. And each expert produces its own output, right? So the final decision is weighted combinations, simply like 0.5 by F1 plus 0.3 by F2 plus 0.2 by F3. And this is implemented using a softmax function in the actual gating network. And of course, all experts can remain active, or maybe we can select, or you can just specify the how many experts you are going to activate. So in our air quality problem, different pollution regimes behave differently. So instead of forcing a single model to learn everything, we allow different experts to specialize in different regimes. So that is the structural motivation for using of this mixture of experts model. So now go back to another equation. So when we just formalize the mixture of expert model, the final prediction is defined as G multiplied with F summation of these values. So F is the output of the case expert, and ZK is the gating function that assigns a weighted to each expert, and K represent the number of experts. And the gating weights should satisfy like a OR summation of the Z value should be 1. This means that the gate produces a normal distribution over experts, typically implemented using a softmax function. So this means that like each expert FK learns a specialized mapping, and the gating network GK decides, and for each same input for the G and F, and how much, and then G just determine like how much each expert should contribute. So final output is a weighted combination of expert predictions. So key insight using mixture of expert is like instead of increasing the capacity uniformly, mixture of expert allocates capacity adaptively based on the input characteristics. So this makes it particularly suitable for regime-dependent problems. Yeah. So now instead of completely replacing a baseline model, we introduce residual formulation. So the model is defined as a function FTCN X, which acted like a generalist, and then G acted like a project manager, and F acted like FK acted like a specialist. So key idea is instead of asking experts to predict everything from scratch, we let them learn correction to a strong baseline. So the baseline is preserved and experts only activate when necessary. Why this matters, like in a long tail regression, the baseline performs well in high density region. So rare regimes require targeted like corrections only, and residual MOE allows like a stability in common cases and also adaptation in extreme cases. Then maybe you can think of it as like the generalist gives an initial estimate, and the specialist intervene only when the regime demands refinement. In that case, like a gating network determines when and how strongly they intervene. So technical advantages of this one is residual running is improved optimization stabilities, and also reduce the interference between the experts, and also prevents catastrophic replacement of the baseline knowledges. And also we can definitely use the simpler model for app, so we can reduce calculation cost as well. And then strong plot line for this slide is like a residual mixture of expert combines global consistencies with the local specialization by using the both generalist information and specialist information simultaneously. So this slide shows the actual architecture used in our study. The input feature Z is fed into the baseline model F base, which provides the general prediction, and multiple expert networks, each learning a specialized correction. The gating network produces the normalized weights, deciding how much each expert should contribute. And the final prediction is baseline output plus a weighted sum of expert corrections. So instead of replacing the baseline, experts only learn residual adjustment. So paper, for this work, like this is the, we already submitted to the MPJ Climate and Atmospheric Science a few days ago, and currently under review now. For the training part, so simplicity, I skipped many implementation details and hyperparameters here because hyperparameters for the residual mixture of expert model is a lot more than 20 or 25, just tuning your model, not the exact hyperparameter for your gate model and baseline model and each expert model. So The total loss consists of the two main parts. First, weighted mean square error, and also expert loss plus gate loss part. So first, the main prediction loss, we already defined this as a LDS-based weighted mean square error, right? So it ensured that rare target regions receive the large gradients, and this term trains baseline model experts and gating network through the backpropagation. And each expert only contributes to the final output through the gating weights. So if for a given input, the gate assigns a high weight to expert K, then the gradient following back through that expert is larger. So if the weight is more, the expert receives almost no update. So experts specialize naturally when an expert consistently receives the high gate weights in certain regimes. So it becomes responsible for those regimes. In other words, specialization emerges from routing-dependent gradient flow. And maybe someone can ask what exactly balance and entropy rules, but balance prevents all input from collapsing to a single expert, and entropy loss increases smooth routing during the training, avoiding the unstable hard assignments too early. So these terms stabilize expert competition. So anyway, experts are trained end to end, but they only receive a gradient proportional to how often the gate selects them. So this creates regime-aware specialization without explicit labels. Okay, we only have just part 3. Excuse me. Yeah, let me briefly highlight the quantitative gains. So first, moving from the CNN to TCN plus DIR. DIR represent library dispersion smoothing, and applying weighted loss only already gives us substantial improvements. And this shows that reweighting the data distribution reduces imbalanced bias. Then adding residual mixture of expert further improves the performances. R-square increases from the 0.8 to 0.88, and mean square error drops by about 37%. And mean absolute error also decreased consistently. So this second improvement comes not from the read weight, but from the increasing the hypothesis flexibility through regime-aware specialization. So the gain is structural, not incremental. And here you can see the structural difference. CNN clearly underestimate the high PM2.5 values here, and TCN reduces biases a little bit more, but still compress the extreme values. And then TCN plus DIR plus our residual mixture of expert corrects the upper tail. Yeah, so the high concentration region aligns much closer to the slope as a one line. So this confirms that improvements is not just average error reduction, it is a specifically tail correction. Is our main objective for this approach. So now what drives the gating mechanism? So I retrained the just gates. So when these gates activate the specific expert, so I try to understand like which parameters are acted important to lore to decide this gating mechanism. So here we see the thermodynamic variables dominate the gating mechanism. For example, T85 50 is the air temperature at the 850 hectopascal pressure level, representing lower tropospheric thermal structure, and T10 meter and QB10 meter specific humidity and near surface the air temperature at 10 meters. Right? So these variables describe atmospheric stability, moisture, and boundary layer conditions. So the gating network primarily responds to the thermodynamic states rather than directly to the aerosol mass. Of course, this does not mean that like our baseline model important feature for baseline model. For instance, baseline model still consider that these aerosol parameters are very important to estimate the forecasting value. These gating feature importance is only for selecting the which expert should be selected for specific input cases. So when I just compared all the values, just averaging or using the standard deviations and try to understand which expert acted or activated or which conditions activate this specific expert. So through the various repeated process, I found that number of 4 experts is good enough. And then each expert captures a distinct physical regimes. So for instance, E1, high humidity and weak wind cases. So I just defined this expert as a marine humid stagnation. And E2 is activated when high temperature and precursors. So I just assigned as a urban secondary formation. And E3 is a strong wind and advection, so I just name as a transport-driven events. And E4 is mixed transitional regime. Importantly, these regimes are not manually labeled, automatically trained from the repeated process. So they emerge from the routing behavior, and geographically we observed consistency. For instance, Ho Chi Minh City, E1 dominantly activated, and Beijing, E2 dominantly activated. So experts align with the physical interpretable process already. This is kinds of like unsupervised learning process because we didn't label the gate. For instance, you should be activated for this specific cases. Of course, you can design your gate as a supervised learning process. So maybe you can specify the conditions like if else statement, for instance, PM2.5 is less than, pressure value or temperature value less than this one. Maybe you can train or activate the E1, something like this. And then we also further tested robustness using the one at a time perturbation for sensitivity analysis. So high gating importance variables also show strong output sensitivity. For example, T500 and T10 meter produce large prediction shift. Meanwhile, aerosol mass terms show limited sensitivity. So gating importance reflects real predictive influence. So this result is very similar to what I did for the Gini feature analysis. Like a thermodynamic parameter is very important for activating the gate. Yep, this slide shows time series of forecasting performances across diverse cities, Dhaka, Hanoi, Abidjan, Seoul, Sao Paulo, and Washington, D.C. Residual mixture of experts consistently improve peak capture for the high pollution cases without destabilizing the low concentrations as well. And this demonstrates like a global residual mixture of expert model can capture the global stability and also extreme event reliability. Okay, this is my last slide. The key idea is the structure, right? So imbalance mitigation requires 2 changes, change of measure by applying the deep imbalance regression approach, just simply reweighting the data distribution, and change of the hypothesis class, applying the residual mixture of experts, increase like regime aware capacity. So we can handle the tail reliability improvement and also just dynamically allocate to rare atmospheric regimes. That's all I have for today. And thank you for your time and thank you for your attention. I'm open to any questions or suggestions.